Bismillah ar-Rahman ar-Rahim. Today we will discuss the gas laws. First of all, I want to mention something that I had missed to tell you before in the previous lectures. First of all, high pressure units as the kilopascal and the bar are not affected much about the gravitation forces that was affecting the level of the mercury or the liquid manometers, nor it's affected by temperature. This is the benefit of this high units of pressure. On the other hand, in the volume and flow measurement, I didn't mention the ball that's used instead of the bobbin. The ball, of course, gets read from the problems of static electricity, where I can read the height of the level from the middle of the ball. On the other hand, I kept saying in the non-differentiated or method to measure the carbon output from a fixed principle, kept on saying oxygen correlated to the end-tidal CO2. So I mentioned, of course, carbon dioxide. I also said that the paddles of the electronic flow meter are made of slits. Of course, they are made of plates in these paddles. I wanted to have a look about the first slide. Of course, the slide downwards. It will be mentioned later on, which is the filling ratio. I want to have a look on the isotherm, which we'll mention later on, to notify the the critical temperature of nitric oxide, which is 36.5, where we find this curve correlating volume to the temperature. I want you to notice that below the critical temperature, the nitrous oxide is a vapor, as you can see, and above it is a gas. This is the first slide we will discuss about. Is the molecular theory of the gases, of the matter, whatever. Matter, of course, as we was shown in the previous slide, is made either from solid or liquid or gas, and we can add also a plasma, which is ionized, as we showed it in the previous slide. So we have the molecular theory stating the difference between the three items. Of course, solid, the molecules are much attached to each other, and the movements are limited, and they, of course, never change their shape. The forces of attraction between the molecules is called lattice. On the other hand, liquid, of course, the relationship between the molecules are much less attached, and the forces are called van der Waals forces. Of course, when I apply heat to the liquid, it's been vaporized to a gas. As you can see from the figure, a container where do we have a liquid and a gas. The liquid is being shifted to a vapor, and the vapor above it returns back to the liquid. There comes a point where the amount entering equals the amount of leaving the liquid. At this point, we call the vapor pressure above the liquid is saturated. See? What is boiling point? Boiling point whenever the vapor pressure, which is above the liquid, equals the atmospheric pressure. Now we come to the main gas law. The first gas law, we call it the first perfect gas law, because not most of the laws are correlated to the gas are slightly deviated, apart from nitrogen, which contains only one electron, and we have one protein. The first gas law, as you can see, is syringe. We have a syringe where we decreased its volume. Of course, the pressure was increased from 100 to 100, as you can see, and we can see the relationship between the pressure and the volume, which is inversely related. And then whenever I want to shift it to an equation, I call PV equals constant. With this constant, we call it constant 1. And this is the first perfect gas law. What's the meaning of constant? Whenever I multiply both at any situation, the pressure and the volume, it's equal. That means that P1 V1 equals P2 V2 and so forth. You see, whenever I want to state the statement of equation, I begin with the constant. So I say the Boyle's law, or the at a constant temperature, the volume of a given mass of a gas varies inversely with the absolute temperature, and we will mention what's the meaning of absolute temperature. We must include it in the statement. What's the clinical application of this first gas law is, as you can see, an oxygen cylinder. Oxygen cylinder is 10 liters, or in other words, it contains 10 liters of suppose oxygen. The gauge pressures above it is reads 137 kilo. I'm sorry, bar. If we want to reach it to a kilopascal, we multiply by 100, so it will be 13,700 kilopascal. So we have two items. We have a pressure and we volume. Okay. Now, whenever I open this cylinder to the atmosphere, the gas becomes released and working in an atmospheric pressure, which is 1. So simply speaking, P1 V1, which are the figures present in the cylinder, equals P2 V2, which are the units present outside the cylinder. So we can simply figure out how much this cylinder of nitrous oxide of 10 liters can yield around 1,380 liters. How that this equation came through? First of all, the gauge pressure, which is the pressure present on the manometer, when the cylinder is full, it reads 137 bar, or 3,700 kilopascal. Okay, this is what we call the gauge pressure. But in other words, if this cylinder is being emptied completely, the gauge pressure will reach 0. But still inside the cylinder we have 1 atmosphere. Otherwise, the cylinder will be compressed. Of course, we can yield this if we cause some sort of suction. You see, so actually speaking, the absolute pressure of the cylinder will yield the gauge plus 1 atmosphere. So instead of being 137, it will be 138. So we have a pressure which is 138, and we have a volume of 10. Both of them are, of course, constant. In other words, when the oxygen is released from the cylinder, it works at 1 atmosphere. So 10 multiplied by 138 equals 1 time how much? By crossing, we can figure out how much oxygen is utilized whenever it's released outside. So we can find it will yield around 1,730 liters. So this cylinder can give me this amount at the atmospheric pressure. So if I know how much I am consuming oxygen in 1 minute, suppose 6 liters, 3 liters, I can calculate how much this oxygen will stand for. You see, this is the first application of the first gas law and first application. The second one, first of all we said volume and pressure. The second one, volume and temperature, and the last one will be the temperature with pressure. You see, so the second gas law, which we consider the Charles or Gay-Lussac, both of them at the same we have the same statement. States that at a constant pressure, as we said before, we must mention the constant first of all. A given mass of a gas varies directly with the absolute pressure. So we have a direct relationship, and we have here an inverse direction. So the equation will be a fraction. So V on T equals constant. This is the second perfect gas law statement. You see, what is the importance of it? Whenever I heat a gas, it becomes less dense. You see, this is the way, one of the methods how we lose temperature, by convection current, where the gas surrounding of us, it becomes heated, and then it descends, getting more air nearby for carrying more heat from the base. This is what we call a convection current. And also, when I heat the helium in a balloon, it becomes this dense and it elevates. The third gas, perfect gas law, we also say that at a constant volume, the absolute pressure of a given mass, we say also absolute pressure. So you must not forget including the absolute in the statement, varies directly with the absolute temperature. This will yield, of course, a fraction. And as we said before, and we have a third constant. So we have three constants. What is the clinical application? Is the hydrogen thermometer. This is the clinical application. Hydrogen thermometer is a special thermometer where the volume is constant in it. You see, and whenever I heat and the heat yield increase in the pressure, this pressure is correlated to, of course, of the temperature. This is why do we use hydrogen, because it's almost the gas that fulfills the items of the gas laws, or in other words, it's the perfect gas. The point after that we'll discuss is the adiabatic changes of state or any gas. In the gas laws we mentioned before, the change of the statement of the gases needed heat or it yields heat. You see, this heat is coming from the surroundings, but adiabatic changes in a gas, it changes, but this energy is utilized from the molecular energy of the gases, the kinetic energy of the gas. So in case we fill a cylinder by gas, by compression, it yields, of course, the kinetic energy increases, it yields a very high temperature, so that we must have a method to decrease the temperature, a cooling method. On the other hand, if we open the cylinder suddenly to a pipe system, this gush of gases will, of course, induce a high temperature. This high temperature, of course, has problems. So we must also have a cooling system. On the other hand, if I release this compressed gas and allow it to expand suddenly, it will overcome the van der Waals force of the molecules and will cause a cooling. This is the principle of the cryoprobe, as we can see from the figure. The cryoprobe is a probe where the gas are being transferred through a very tiny tube, and it comes out in a way that it overcomes the forces, yielding a very low temperature, as you can see, minus 70. This is used, of course, to remove some sort of wars, or in ophthalmology and gynecology, and to relieve pain, suppose in thoracotomy, where I can apply this nitrous oxide cooling effect on the nerves. This is capable of to destruction only the sheaths of the nerves, and after 6 months it regains its property again. After that, we will discuss what we call Dalton's law of partial pressure. In other words, if I have a mixture, this mixture contains many gases. Each gas will exert its own pressure irrespective of the other. In other words, if I take each of the gases in the mixture and put it in a special container, it will yield the same pressure. You see? So we have a clinical application, as we can see. We have the Interlock cylinder. Interlock cylinder is a cylinder made of nitrous oxide oxygen 50-50, both in a gaseous state. These are used, it is used in alleviation of pain. The pressure of this cylinder is 100, and as long as each of them is 50%, so each of them will yield 50% of that total pressure. You see, so if we take each of the gas and put it in the same cylinder, it will yield the same pressure, though the volume working of the gas is increased. But if we use Boyle's law, we can notice that instead of being 100, because we are increasing the volume, the pressure will be 50. So there no change will occur. So the pressure in the mixing gas is equal to the pressure whenever it is in a lonely gas. The second thing is the oxygen, the air cylinder, where we have oxygen and nitrogen. Of course, oxygen most probably is around 20 and 90.93%, and nitrogen is around 79.07%. This 2% yield a pressure of 100 kilopascal. So if we take each of gas and we put it in a separate cylinder, each of them will exert the pressure that they had when they were mixed. So because it was 100, and each of them, when they are separate, each of them will yield 50 because the volume is increased in this cylinder, because it occupies there is much occupying space for this gas to move. So whenever I can use Boyle's law and Dalton's law, I can figure out the tension of the gas in a mixture. And as long as I know the percent, I can utilize it to know the tension of the gas. So whenever I have a gas of oxygen which is 20.39% in a cylinder, of course I can figure out simply that the oxygen partial pressure will be 157 millimeter mercury. You see. The point that I must mention, of course, how do we fill a carbon dioxide cylinder? A carbon dioxide cylinder was a cylinder having 10% oxygen and 90% of carbon dioxide to stimulate the ventilation, so to enhance the induction of anesthesia. So how do you use to utilize the Dalton's law? Okay, I know that the cylinder is 100% whenever it's full, and then I apply carbon dioxide till the pressure of the the gauge reaches a certain limit, knowing that I had filled the cylinder but at a certain limit, and then the rest of the cylinder can be supplied by oxygen simply after carbon dioxide. You see, from the Dalton's law, I'm knowing the percent of carbon dioxide and oxygen in this cylinder. Of course, whenever I want to do a proper estimation of the partial pressure, I must put in my mind whether I'm using or we are using in a humidified area or not humidified area. So properly speaking, whenever I want to estimate the carbon dioxide tension, I must subtract the water vapor tension from the total, which is around 6.3 kilopascal. So whenever I abstract it from the total, which is 101.3, I yield the partial pressure, or I yield the pressure without the water vapor, and then I multiply by the percent of carbon dioxide, which is 5.6, and I will gain lastly how much carbon dioxide most probably is present in this mixture of gases. The next slide will begin about the Avogadro's hypothesis. Avogadro hypothesis being summon iftiradi. We can see two cylinders, the two syringes, I'm sorry. The two syringes have the same temperature, as you can see, and the same pressure, not standard temperature and pressure, see? So we have equal volume of two gases. These two gases are different in their molecular weight and their mass, yet they have the same number of molecules, see? So the statement of Avogadro's hypothesis say that of course, it contains V. So we begin the statement by volume. So equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. You see? So this is the first item about Avogadro's hypothesis. On the other hand, the mole of A, what's the meaning of mole? This is the way to express the amount of substance. As we said before, the substance we mentioned before of gases have the same, though they are different in the molecular weight and their mass. Their number can be used to estimate this quantity. So we say whenever I want to know the amount of substance, I use what we call the mole. The mole, in a simple word, is the molecular weight of a substance in grams. In other words, if I want 1 mole of suppose of oxygen, I get 32 grams of oxygen. This is 1 mole. You see, it was noticed 1 mole of any substance at the standard temperature pressure. Remember that contains the same number of particles. These particles you must memorize 6.022 times 10 to the power of 32. This must be mentioned, memorized, you see. So any mole of any gas occupies contains the same number of moles. In other words, 1 mole of carbon 12, which represents 0.01 kilogram of carbon, which is 12 grams of carbon, equals the same number of molecules present in any mole. So you can see a weight, and this weight I put 12 gram at 12 grams of carbon 12, or in other words, I put 0.01 kilogram of carbon. This is 1 mole. So this amounts of particles are present with any mole at standard. Now we come to a point. 1 mole of any gas at the standard temperature pressure, remember this, occupies 22.4 liters. In other words, if I get 1 mole of a gas, suppose I get 44 carbon dioxide or nitric oxide, have the same molecular weight, and then I spread it in an atmosphere where the pressure is 1 atmosphere and the temperature is 0, or 273 Kelvin. So the gas will expand till it reaches the point where it stops. This amount is 22.4 liters. You see? We utilize this point in calibration of a vaporizer. We have a vaporizer where we put the isoflurane. We get 1 mole of isoflurane, where a molecular weight is 1845. You see, so this is 1 mole. If I put 1845 gram of isoflurane in this container, I put only 1 mole. So if I use the tenth of it means I'll use 18.45 gram of isoflurane, or grams of isoflurane. I put it in the cylinder. So we have 1/10 of a mole. This 1/10, how much it will occupy the standard temperature pressure? It will occupy 2.24 instead of 22. It is the 10th of it. You see? Okay. Suppose I want to give 1% of this isoflurane. I adjust it up to 1%. How much of a carrier gas must go through this vaporizer to take the 100% concentrated isoflurane to be 1%? If we figure it out simply, we can find that we are in need of 224 liters of carrying gas to pick up 1% of isoflurane. So this is the clinical application of Avogadro's hypothesis. Or always remember that the statement that we said in 1 mole occupies 22.4. It acts at the same, or the standard temperature pressure. But what we had said before is not in the standard temperature pressure, where the isoflurane is in the room temperature, so we must compensate for it. On the other hand, the nitrous oxide cylinder, well known that whenever I want to know how amount of nitrous oxide is present in the cylinder, I must know it by weighing. Why? Because part of it is in a gaseous state and part of it is in a liquid state, so I cannot depend upon the gauge to measure the amount. So suppose we have a nitrous oxide cylinder where the amount of carbon dioxide in it is around 4.3 kilograms of nitrous oxide. How much will it yield of nitrous oxide whenever it's exposed to the atmosphere? This is the point. Simply speaking, as we know, the molecular weight of nitrous oxide is 44. So what's the meaning of 44? Knowing that it's 44, that's 1 mole. It occupies 22.4. So we have 4.3 kilogram. How much of it contains 22.4 liter? So this is a simple method how to figure it out. This is around 1,730 liters, where oxygen, never forget, yields 1,380 liters. See, this situation occurs in the room temperature. But in case of a standard temperature pressure, as we said before, this in the standard temperature and pressure, I'm sorry, but actually speaking, this is the figure that occurs in the at the 15 degrees Celsius. Why? Because it's 15, it's not 0. You see, the weight, the weight of nitric oxide in a full cylinder is called tar weight. The universal gas equation, or the universal gas constant, whenever I put the three equations each other and then I figure it out, it will be PV over T will be constant. And if we apply Avogadro's, we add Avogadro's hypothesis to the general gas law, we can yield this figure, PV equals nRT. You see, this is, it will yield the gauge of the cylinder, gas cylinder. Of course, if the pressure is constant, and the temperature is constant, and of course the R is constant, you can correlate the pressure to number of moles, pressure to the amount of gas present. So the gauge pressure is being transferred to what we call content gauge. So the gauge or the pressure of the gauge gives a hint about the amount of oxygen present in the cylinder. Critical temperature, of course, each gas has its critical temperature. What's the meaning of that? Whenever I fill, as we can see from the figure, the nitric oxide cylinder at room temperature of 20, by time, as long as it is gas, it will keep on elevating the gauge till it's being transferred to a liquid. At this point, which is 36.4, at this point, the nitric oxide will be shifted to the gas, so the gauge will not correlate much with the amount present in it. On the other hand, if we use oxygen at the room temperature, of course, all the time it will be a liquid. So the gauge will give me a hint about the amount of gas present in the cylinder. Of course, the critical temperature of oxygen is minus 119. You must, of course, remember that. So it's very difficult for it to be transferred to liquid in such circumstances. And now we are going to talk about isotherm. Isotherm is the correlation between volume and pressure of nitric oxide at different temperatures, called isotherm, which will give me a series of lines. This series of lines at 40 and 36.5 and at 20, as we can see from the figure. First of all, the first one applies gas law because it is completely gas. As we find the syringe, we decrease the volume, the pressure increase, causing what we call rectangular hyperpolar. On the other hand, whenever we reach the critical temperature, as you see, we are decreasing the volume. As long as we are decreasing the volume, the pressure increases. So on the graph, at 36.5, the pressure is slightly increased, and then we come a point where the liquid at the pressure of 7.2 is transferred to liquid. At that point, whenever I decrease the volume, the pressure will increase abruptly, as you can, not slowly. This is why, because it's transferred to a liquid. You see, on the other hand, with the most important, interesting line, which is the nitric oxide cylinder at the room temperature is 20. As we are decreasing the volume, as you can see simply, and then it's transferred to a liquid. But at this point, at the pressure of 52, the decrease in the volume at this point along this line, it does not much change the pressure. The pressure is constant. Why? Because at this point we have in the cylinder a gas and a liquid, a combination. The gas by time, whenever it's transferred, shifted to by condensation to a liquid, and the liquid is shifted to a vapor to replace in case we use the cylinder. At that point, the equilibrium, this causes the pressure to be constant in respect of decrease of volume. This is why we have a straight line instead of a change in the pressure by change of volume. Whenever we say the critical temperature, we consider one gas, but special circumstances we have mixed gas and the interlocks. Interlocks means there are two gases mixed with each other. They both are in a gaseous state. You see, so we call what we call pseudo-critical temperatures, the temperature where both of them separate. You see, it's around minus 5.5 in the interlock cylinder and around minus 30 degree in the pipe system. So simply speaking, we must take care when we use this cylinder. We must elevate the temperature or put the cylinder in a transverse position to assure that the temperature is not much less than minus 5.5. Otherwise, we will have the nitric oxide change to be a liquid, and we will have problems that we will mention later on. The last point to be mentioned, we had written in the first slide, is what we call the filling ratio. Of course, assuming that theoretically or hypothetically case, if in case of suppose all the cylinder of nitric oxide is liquid, so whenever I heat this liquid, it's not easily compressible. Some of it is being shifted to be a vapor, but there is not much space for it to increase, and it will yield problems and explosion. This is why whenever I fill a cylinder, I must fill it to a certain limit. This is based on what we call the filling ratio. What's the meaning of filling ratio? Filling ratio is simply speaking that I consider the amount of water filling the cylinder. Suppose it is 10 liters of water, and as we know, 1 liter of water equals 1 kilogram. So we have a mass of 1 kilo, suppose 10 kilograms or a kilogram of water filling the cylinder. Okay, how much of nitric oxide ought to be used in such circumstances? In England, we use what we call 0.65%. What's the meaning of that? In a proper way to fill the cylinder with 65 only percent of the 10 that we have mentioned of water. In other words, the filling ratio is the mass of water to the mass of gas. You see, we must make a ratio. This ratio assures that we have a proper amount of nitrous for fear of explosion. And thank a lot, and I hope that I succeed. Wassalamu alaikum wa rahmatullahi wa barakatuh.